And then at the end of the class, I know many more of you are here today because I said I'm going to hand out the exam books. So you can line up at the bottom at the end of the class, and we'll hand out the exam books, okay? So here's the way to think about this course. In the first half, before spring break, other than packet loss in the internet, other than that one small source of failures, we considered a world in which there were no failures. The servers didn't fail, things didn't fail. You worried about how to make things work correctly in the absence of failures. And that was hard enough, right? Murphy had plenty of room for maneuver, even when, there were no failures. So you can imagine how much more complicated life is when there are failures, okay? The good news is that over multiple decades, as a community, we have learned how to build distributed systems that actually work, even when components fail, even when servers fail. So the systems you use today, every day, Facebook, Google's various services, Amazon cloud services, and so on, they all embody the things that you'll learn about in the next few weeks. Okay? So it's going to take us a while because there's a lot to unpack. And we're going to work our way from the bottom upwards. But before we do that, I want to take a moment to help you understand what exactly we mean by a failure. If we're going to spend many weeks working on this, and you're going to do a project on it, let's get it straight. Okay? So what is a failure? A failure is some kind of deviation from specified behavior. So if you're driving a car and you turn the steering wheel to the right, you expect the car to go to the right. If the car turns to the left, you're in bad shape. There is, in fact, a company that makes bicycles precisely that way. When you turn the steering wheel to the right, the bicycle actually goes to the left. Its purpose, supposedly, is to help you unlearn behaviors you've learned from childhood with the goal of reprogramming yourself. That's a whole other separate weird concept. In the real world, when we say specification, you turn the wheel to the right, the car turns to the right. You press the brake pedal, the car stops, right? If you're a pilot in an aircraft, you pull the stick forward, the nose lifts, and so on. These are specified behaviors. Now, in many cases, it turns out that when you think something has failed, the problem is not that it's not following the specification. It's because you didn't fully appreciate the specifications that were wired into the system. Now you might think, how is this possible? I designed the damn thing, I implemented it, how could I not understand it? It is possible. It's possible when you have a complex algorithm which you use as the specification, and you don't fully understand the subtle corner cases of that algorithm. And so when the system behaves a certain way, you assume it's a failure, but in fact, it's not a failure at all. What it is doing is in fact carrying out precisely what it was expected to do. So this is an important point, right? As we look further, we'll have to look very carefully at what constitutes specified behavior. Now, there are many things that can fail. Obviously, the hardware can fail, right? You just saw a proof. This little gadget wasn't working. It's worked for every class since the beginning of the semester. Before your very eyes, you saw a demo. The environment could fail. This room could catch fire, or the air conditioning could go out, or the lights could go out, or the power could go out, etc., etc. People can fail. All right? I could have made a mistake in the connections, or Kevin could have made a mistake in the connections. There could be nothing wrong with the hardware. And of course, you all know, software can fail. You're writing the software, there can be bugs in it. If you deploy it with those bugs, they're going to manifest themselves. So in the face of so much possibility for failure, how exactly do you build a failure resilient system? So the deepest insight into this was actually written almost, 1962? 60 years ago? Yeah, exactly 60 years ago. In a very nice essay. This is actually in your optional reading. It's worth reading for many reasons. One of which is what it has to say about failures. Right? So Herb Simon, after whom Newell Simon Hall is named, was one of the founders of this School of Computer Science in 1965. And he won the Nobel Prize for Economics in 1978, the Turing Award many years before that. He was one of the co-founders of artificial intelligence. So very interestingly, he made this observation 60 years ago. Remember, the only computers that existed then were mainframes, right? Big monstrous things that took up the size of this room. That these systems have a property which he called near decomposability, that greatly simplifies their behavior. And you're going to see this point made a number of times in the next few lectures. Keep this in mind, near decomposability. If it's perfectly decomposable, it's not a distributed system. Right? There are different silos independently working. A distributed system does have clients, it does have servers, it does have users. It may have multiple servers. Somehow they all work together. But they're not too tightly entangled with each other. That property, how to find that sweet spot, is precisely the point of near decomposability. In that paper, there's a wonderful story. It's a parable he tells. Imagine two watchmakers. Right? They make very complicated watches. Each one requires 1,000 parts, tiny little pieces. They all have to be put together perfectly for the whole thing to work. The first person assembles the whole thing. Halfway through, it may take him many days, halfway through, if he's interrupted or something happens, he has to start all over again. If he accidentally drops the pieces on the floor, you have to start from scratch. The other guy divides up these 1,000 pieces into sub-assemblies. This module, and then this module, and then this module. And he puts the parts for them separately. And he assembles one module, puts it away. Assembles the second module, puts it away, and so on. Now if he's interrupted, he loses the thread of work on the current module. He has to restart that. But he doesn't have to go back to square zero. He only has to restart the current module. So modularization, which you've all learned from the very first class at CMU, turns out to be crucial. Because what it does is it bounds the amount of work that has to be redone upon failure. What is the name for this phenomena from before spring break? Does anyone have? Where did you see this? Same idea. Except I use different words. Yes?
Failure independence?
Failure?
Failure independence?
Failure independence is what this is about, yes. But there's a particular property, a particular way of reasoning. It was called the end-to-end argument, remember? The fact that I can send this gigabyte file in one fell swoop, or I can send a kilobyte, have the acknowledgement, send another kilobyte, have the acknowledgement. Now, if I don't get the acknowledgement, I only have to resend the most recent part. That is the same idea. Apply that idea on steroids, and you have the fundamental building blocks of what it takes to build resilient systems. Okay? So how do you layer resiliency? As I just mentioned in the previous slide, code and data have to be modular. That's a given. You somehow have to split them up. The way you build these systems is you have layers. At the lowest layer, someone somewhere has to detect the failure. It's a deviation from specification. So if I'm transmitting on TCP and I get an exception, that's a failure that has been detected for me by TCP. Sometimes I may have to check a return code rather than have an exception generated. So exactly how you detect failures is very, very domain specific, but detecting it is what happens at level I. One level above, the job is to clean up the mess that has happened at this layer. As you know, in the real world, you spill a bottle of milk, the floor is a mess. You drop orange juice, or worse, you drop honey, it's sticky, right? It's a mess. Before you can do anything else, the mess has to be cleaned up. That cleaning up of the mess happens at a layer above, and then you hide the fact that the mess even happened. And so the layers above are completely unaware that all these bad things happened. So much work had to be done. The layer above only notices one thing. They notice this request somehow seems to be taking much, much longer. We don't know what's going on. What they don't know is that their request triggered a bug on the server died, some other system had to detect the death of the server, had to clean up the partially executed state, that took many minutes, and then a new server had to be launched, that took another few seconds, and finally your request was serviced. So all you notice is an inordinate lengthening of the time it took to execute your request, but otherwise it's perfectly fine. Notice that you've seen an example of this idea also in RPC. What was it called? Retransmission. Yes, retransmission is the mechanism you use, but the property that embodied this concept, that you don't even see the failure, was in exactly once semantics. Right? Because the fact that something died, something had to be restarted, 2 years later, you get the acknowledgement you've been waiting for. It's okay. It's exactly once. It worked. The fact that it took 2 years, okay. It's like finding Shackleton's ship Endurance after 100 and whatever number of years. Right? It made it finally. So this concept of detection, confinement and cleanup, masking, and then layers above being invisible is basically how all of these systems work. So let me walk you through a few examples. If you have TCP, which you've all studied in the earlier part of the course, packet loss happens at a certain layer. The kernel implementation of TCP sees this packet because it doesn't get an event. So it detects it. There's not much to clean up in this case, fortunately, because it performs the action, retransmission, and hopefully this time around it works. And your application doesn't even know the packet was lost. All it knows is that the bandwidth you're getting, the throughput you're getting, is much worse. It could have been due to many reasons. Maybe packets were being lost. Maybe the bandwidth on the internet was low because of congestion. Could have been any reason. You don't know, and it doesn't matter. The behavior, it's undetectable in the higher layers what happened in the lower layers. On a disk, you have an ability called bad block mapping. So SSDs also have this property. You can only write to them so many times. After that, they're unreliable. On magnetic disks, it's a little more random, but because of manufacturing defects or other defects, it's possible that the incredibly thin layer of magnetic material somehow loses the ability to retain the state that was given to it. This is serious, right? It means in the middle of your file, bits have vanished. Not good. So, bad block mapping involves detecting that this is happening. That's the failure detection. The cleanup typically involves finding another unused portion of the disk, marking it, and giving it the same address as this one. And typically, certainly on magnetic disks, but this is also true for SSDs, when you format a disk and say, I want it to have ext4 file system, or I want it to have NTFS file system, part of what's going on also includes reserving a portion of the storage for bad block mapping. Right? Up front, you set aside, you don't use those blocks, so that in a future time, if you ever have to find spare space in order to do this block mapping, you can actually do this. Okay? The device drive and the operating system are unaware that all this has happened. It can all be implemented at the controller, or in some cases even in the disk firmware. The Coda file system is a highly resilient file system that was built here at CMU by my research team, and it uses the same concept. When a server dies, the client code, the cache manager, knows to switch to another server. It has to detect the death of the server, do the switch, and then applications that are running on top, all they see, I tried to open this file, and instead of just immediately opening it, it took many seconds. What I don't know is behind my back, all these things had been done to make it possible. So, there are limits, obviously, to how well you can do this, okay? Not every failure on Earth can be masked. So a simple example. If I am disconnected, I have no network connectivity. I'm on a plane, I'm flying over Alaska, maybe from one of the Asian countries, South Korea, China, somewhere, right? The flight takes you over the Bering Strait and Alaska. And believe me, I've flown that route many times. And if you get Wi-Fi on the plane, the ping times are typically well over 1 second when it works. And many times there are dead zones where there's no connectivity. If you get a cache miss, you're out of luck. There is no way to handle your cache miss. Now, if you have an RPC mechanism which implements exactly one semantics, it will block on that cache miss, waiting forever. And maybe finally, when you've come all the way down and you're flying over Vancouver, perhaps connectivity is restored and your system will continue. If I've at most once RPC, after a minute or 2 minutes or 5 minutes, some timeout interval is going to report an error. And that error is going to propagate and become visible as a cache miss that cannot be handled. And that's the kind of failure that cannot be masked. The only way to avoid it is to be clever enough ahead of time to prefetch all the data that you need. Now you can do it brute force, like Dropbox. So you fetch everything. That way, you don't have to worry. Somewhere in there, out of those gigabytes that you've prefetched, might be the 1 kilobyte that you need. Or you can be more precise and targeted, and you'll see how you can do that later in this class. Okay? Sometimes it is theoretically possible to mask an error, mask a failure, but the cost is too much. A good example of this is cache size. If I have a small cache size, the chances of cache misses are higher. One way to avoid cache misses is to get a bigger cache. Right? We also talked about exactly once versus at most once. Right? That's the difference between being blocking forever and having a timeout. On a disk, how many microns of disk surface can be destroyed without you being badly impacted? The answer depends on the design of the encoding mechanism used on that disk. It is possible to have a lot of the disk reserved for bad blocks up front, so that even if many megabytes got destroyed or look like they're not going to be readable, you can do the remapping that I just described. But this means you took a gigabyte disk and you're only using 500 megabytes out of it. It's very much, the way to think about this is like paying the insurance premium. How much are you willing to pay for your car insurance every year? How much are you willing to pay for your health insurance every year? The answer is it depends on the risk and it depends on the coverage. The insurance company designs this amount in such a way that there's always a profit. So you're always going to lose. But the difference is you have bound the magnitude of the loss. Right? In aggregate, from the point of view of the insurance company aggregated over all customers, there's a net win. But any given individual, your bad luck, Murphy struck, and your car was totaled. So for you, if you didn't have insurance, the loss would be $20,000. Right? It's a huge loss. The fact deductible, $1,000, the other $19,000 are paid by the insurance company. For the individual for whom the impact occurred, it's a win. It's the same reasoning here. We don't know which block might go bad. We don't know which packet might be lost. So in aggregate, you design these systems in such a way as to reserve some of the resources to cover it. But that by itself bounds the extent of the loss that is possible. Yeah, you'll have to sit through the lecture if you want your midterm exam, okay? Unfortunately, that's the only way to get it. Okay. So the bottom line, as I said, is resiliency is never free. If somebody is promising you a system that has no overhead but is robust, they are lying and you are a fool. Okay? Keep this in mind. Your first question should always be, okay, we know there's a price. What form does it take? Is it protocol overhead? Is it additional packets? Is it additional storage? Is it lower battery life? The cost can take many forms. And making sure you look carefully at all the resources in thinking through this is important. When a failure cannot be masked, then it becomes visible to a higher layer of software. So when you get a cache miss, maybe the application that was running was Adobe Acrobat. And Adobe Acrobat was trying to show you a PDF file. Embedded in that PDF file was this weird font that was not cached. And so it reached out to cache that font. And so Adobe Acrobat now gets a return code that says font not found. And the behavior of Adobe Acrobat at this point determines whether you, the user, see this error or it's masked. So if Adobe Acrobat returns to you an error saying, sorry, cannot read PDF file, missing fonts, goodbye, you're out of luck. Because the sender had used some weird font in the attachment, you're not able to read the PDF file. On the other hand, Acrobat could be written in a way that says, you know what? If you can't find a file, assume a default font, like Arial or Times Roman or something. And so then what you will see is a PDF that doesn't quite look like what it was intended, but it's a failure mode that is different from telling you, I can't show it to you. And so it's a design choice for the application designer how you fail. So there might be a warning that tells you, I couldn't find all the fonts, and I therefore had to use a default font for some of these things. So this is the kind of thinking. I've already gone over all of this, so I won't repeat them. So to recap, these are the three key steps: failure detection, confinement and masking, confinement and cleanup, and then the masking step. And we will look at this in greater depth in the next class. I'll have Babu come and tell you about Project 3.
All right, so how was your spring break? Everyone did well? All right, great. So now that we're back, we're here to get back in the swing of things, and we're going to start Project 3 today. So Project 3 is actually going to cover some of the stuff we were talking about in lecture before break, mostly on how systems can be scaled, right? We talk about scaling up systems, right? Scaling up versus scaling out, right? You guys remember the difference, right? Scaling up versus scaling out? Good. So this is all about scaling out. It's actually about how to create a distributed system where you actually scale out different parts of it in order to service larger loads or smaller loads, right? That's what this is all about. So in this project, basically we're going to have a simulated web service. So imagine you have a small storefront of some kind, right? You're implementing some sort of web shopping experience. You create a website. It serves pages that describe the products in your website. And customers can come, browse the objects, browse the products. If they wish to, they can make purchases, right? That's what you want. So, of course, we don't actually want you to write this. This is a very complicated thing to write yourself. So we're going to actually emulate most of this, right? We're going to create an emulated storefront with a very simple quote-unquote web server and a quote-unquote application server that handles the back end of purchasing things. And we're going to run it on a quote-unquote cloud service, right? So remember, the cloud is a way to actually very easily scale out applications, because you can actually dynamically ask, I want a new machine. I want an additional machine that comes in the form of a virtual machine, right? And by creating these virtual machines, now you can run multiple servers very quickly. So we're going to pretend we have such a cloud service here. And of course, since we don't have such a thing on Autolab, we're going to emulate it. So we're actually going to use processes. We're going to pretend each process is a separate VM, okay? So we're going to provide you a library that lets you ask for a new VM, and after some boot time, your VM starts, which is basically another instance of your process, okay? And that's how we're going to run this whole project. Now, of course, we don't have real clients either. So one part of the project code that we provide you is an emulation of clients. So we'll have actually a random set of clients that arrive, and they will try to do things like, oh, I'm going to browse your website, look up what products are available, and at some point they might now create another call to say, I'm going to browse another part of your website, maybe another part. They might do multiple of these calls. And at some point they might decide, oh yes, I do want to purchase this, and then they might make actually a purchase request. Those are different types of requests that could arrive at your server. And the clients are finicky. They expect to have good service, meaning as soon as they make a request, they get a timely reply. So either it's a timely browse request, so you get back what are the products very quickly, or when they try to make a purchase, it goes through within a matter of seconds, right? If not, they get upset and leave, and they won't come back, and then you lose your purchase, right? So your goal is to keep clients happy, right? And one way to keep them happy is keep service time low. And what's one way to keep service time low? Well, to have enough resources in your server set to handle them quickly. But of course, that doesn't come for free either, right? You're paying your cloud service for all the VMs you're using. So if you just keep 1,000 VMs up and running all the time, yes, your clients are going to get great service. But if they just make one purchase today, you wasted all your money on keeping those servers up, right? So that you have two goals in this project. One is to minimize how much VM time you're using. And the second is to make sure you keep as many clients happy as possible. Right? Good so far? So now we come to what is the most frustrating part of this project, but is actually one of the most important. It's not actually the scaling part, but it's the fact that all of this is going to be non-deterministic. Right? And this is actually a key, I wouldn't call it a feature, but a key property of real distributed systems. Even very simple systems like this, where we actually emulate everything, and we actually make each component as deterministic as possible, when you put them together in this kind of a system, it becomes non-deterministic. Very small changes in the order of operation, or very small changes in timing, can actually cause very dramatic differences in behavior. So this is something you'll have to deal with, right? Every time you run your project, it may run a little bit differently. Okay? Yes?
Quick question for the project. Do we have a spin up of VM, or it's turning on a VM to serve or trying to turn it back down?
Yes. So good question. So the question was, is there a cost to spinning up VMs? And the answer is yes. There'll be a time penalty, basically. There'll be, as soon as you ask for a VM, you start getting charged immediately, but it takes some time before you're execute on that VM, quote-unquote VM. So, other questions so far? Yes?
Why do you quote-unquote VM? Is it not a VM?
It's not actually a VM, right? So we don't have the resources to actually provide you a real cloud service. So here we're actually just using processes to pretend like they're VMs. So in fact, Autolab itself is a VM. So you have just one VM, and we're not going to do nested VMs in there and things like that. So it's just using processes, just pretend that they're VMs, and you're good. It's just a simplified model of what you'd see in real life. Okay? Great. So this is what the system would look like for checkpoint 1. And basically, you're going to build a 2-tier system. So you have basically your server, which consists of handling all the web requests and all the application logic, which is connected to a database in the back end. That's it. In the front, there's assumed some sort of a load balancer. So as clients come in, they will be directed to one of the servers you're running. Okay? And so if you have 3 servers, each client will just round robin to each of the different servers. Okay? And of course, when your VM comes up, it has to register with the load balancer with a snippet of code like this that actually tells it to register. And then the main loop is basically going to say, get the next request, and then handle the request. Okay? And since we're not actually writing the real application code, this is actually all you really need to do. So up here we have get request is the front end. So pretend like that's the web server. So all of the HTML processing, all that stuff, that's basically this one line. We're just simplifying it for you, right? And then once you get the application request, you may need to now generate a dynamic page based on their preferences and whatnot and what's available to actually dynamically construct a page using what's available in the database, et cetera, to actually give them something to browse, right? That's just this one line here. Okay? So this is a simplified version of a single application server for this application, right? Handle request behind the scenes will cannot talk to the database. Okay. That's basically it. So if you have this, you have your web server. So we've given you that code already. What you have to do is decide how many servers do you need and when to scale up or scale down. Okay? That's the key goal. For checkpoint 1, we're going to tell you that the load is going to be based purely on the quote-unquote time of day. Quote-unquote because, again, we're not doing this for real, so we're going to just give you a parameter to your system when you start running that tells you what time of day it is. Okay? And the load is just going to follow some sort of a load curve across the day, and this is the one we're going to be using for this project. So at different times, different hour of the day, starting from midnight to the end of the day, the load will vary. And the load here is expressed in terms of new clients per second. Per second? Yes, per second. So based on this load, you have to determine how many servers you need for that time of day. Okay? So the question you might ask is, how do we do this? Any thoughts? How do you know how many servers you need? Yes?
You have a map that explains the number of servers you need at different points. Okay.
Yes, that's correct. So the answer is you create some sort of map, some sort of table. How do you know what the values of that table are, though?
Trial and error.
Trial and error, okay. Yes?
You could start with a reasonable, assume that one server can handle 1 pack per second, and assume that you just plug this map, and then I guess go over down to the server next time.
Sure. So you're saying trial and error, or start with something reasonable and then tweak it until it works, right? Those are all both good answers, but I think for this, we want to be a little bit more formal about it. And so the right formal way to do it is to do benchmarking, right? You actually want to test your system offline to see how well it does with different amounts of load, so you can decide, yes, when there's this much load, I need this many servers. Or conversely, you can say, with this many servers, I can handle up to this much load with decent response time, right? So that's what you have to do, right? To determine how many servers you need. Yes, question?
So is the load curve fixed?
For checkpoint 1, the load curve is fixed. So basically, you want to decide how many unhappy customers you get. You want to minimize that number while still minimizing the number of VMs you need, the number of servers you need, right? So you have to benchmark the system. So what can you do? You can say, okay, let's run my system with exactly one server, right? And I'm going to just try different cases. I'm going to run it with a very low client load, one server, or one new client per every 10 seconds. Can I keep those clients happy? Right? You could try it. You can run it and try it and find out. Okay? Well, I guess I did it the other way. So, okay, for a given load. Yes, go ahead.
For these tests, can we run locally or we have to upload to also that?
You can run locally. That's a good question. So the question is, can you run this locally? Yes, we give you all of the harness to run locally. We don't give you the specific cases we use on AutoLab, but you can run whatever cases you want yourself. Yes?
Would you just give us an integer of how many SaaS clients you have?
The output is, the system when it finishes running will provide you a list of how many clients timed out, how many clients made purchases, how many clients just browsed and were happy, right? It'll give you different categories of unhappiness as well. And it'll also give you how much time you spent, right, in terms of VM time. Yes?
Will there be like a minimum number?
So the question was, is there a fixed amount, or is there some margin of error? So in all the tests, there is no one right answer. So there is a range that's acceptable. The better you do, the higher your score. So I'll get back to that in a second. So again, with benchmarking, you can say, let's pick a certain load. Let's say 1 client per second arrives. Let's try it with 1 server. Let's see what we get. And we can actually plot that, right? We'll say with 1 server, we get X number of unhappy clients. Let's try again with 2 servers. Maybe with 2 servers, we do better, right? So now we have a smaller number of unhappy clients. Let's repeat. 3 servers. Does it get better? What we'd expect, based on some of what we talked about before break, was yes, it should get better and better, right? Up to a point, right? After some point, you're handling all the clients you can possibly handle, and adding servers is not going to help anymore, right? So what would you expect? You would expect, if you plot this, first you have relatively high, then it gets better, and at some point it levels off, right? You should see a curve something like that. The more servers you add, the better it gets up to a point, and then it levels off. So what is the right answer? What is the number of servers you want? You probably want to be near that knee of that curve, right? So you're actually minimizing the number of unhappy clients, or maximizing the happy clients, however you want to say it. But at the same time, you're using as few servers as you can to do that, right? And so you can do that by actually doing a bunch of benchmarks and creating a graph. You can create a plot yourself, right? And in fact, for checkpoint 1, we are required to hand in 1 example of such a plot, right? We're not, you'll have to do a lot more experiments than that to get all the cases, but you want to at least make sure you're going through that process at least once. So you need to hand in a PDF of such a plot with checkpoint 1. Questions? Yes?
You're supposed to optimize the number of unhappy clients, or like that's the first priority, and then after that, you define the number of servers.
Yes, for the most part. I mean, again, it's a little bit non-deterministic, so you can't always do it perfectly. But yes, the idea is that you want to minimize the number of unhappy clients as much as possible. But you have to remember that even in your benchmarking, there's going to be a little bit of a non-determinism. So you see the general trend is like down, 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 basically level. But at the very end, it might be slightly lower. Yeah, you have to kind of approximate, right? If you have the main curve looking like this, a little bit of fluctuation, you shouldn't overweight that small fluctuation, right, when you're doing this. So you really have to look at the trends in your numbers. And it's actually a little tricky. It's actually a good question. It's a little tricky to see. But that's what you have to learn to do, right? Your benchmarking is not deterministic either. Right. There's another question? Yes?
Yeah, so here, like when we're doing benchmarking, do we have to make the servers big enough, like sequential? Because like if you're starting many servers.
Good question. Good question. So in the actual executing system, you'll have to spin up servers sequentially. But for your benchmarking, you can do that statically. You can just say at the beginning, I'm just going to run my code. It's going to just start 3 servers right at the beginning. And that's actually better to do it that way because now you have one less variable that's going to confound, what the numbers mean, right? So you want to keep it as simple as possible for your benchmarking. So one way to do that is you turn off all of your auto-scaling capability that you put in your system. Just run it with a fixed static number of servers, figure out what it is, and then now you know that, maybe with 4 servers you can handle this particular load. So the goal is when you make it auto-scale, you want to make sure that with this kind of load or with this time of day, your system will reach 4 servers, and quickly, hopefully. Other questions? Okay, so that's for checkpoint 1. So what's different from checkpoint 2? So checkpoint 2 uses a slightly different system, right? Here, we're actually going to do a 3-tier service. So we're using a service where the front-end operation, so the web server, is separate from the application server. And then you still have a database in the back, okay? And so now what advantage this has is now each tier can be scaled independently. So it might be that with the front-end service where we're just doing the GET request calls only, you can maybe handle more clients on a given server, right? So you don't need as many of those. But you may need a lot of app servers to handle that load. So you have to try to benchmark to see how many front-end servers, how many application servers do you need to handle a particular load. So the benchmarking becomes a little bit more complicated, and there's a little bit more interaction between these two. You also have to decide how you're going to do the RPCs between the front end and the back end, right? That's also something you do. To make sure you're not just writing the same code, there is a penalty for using, time penalty, not points penalty, time penalty for using both the front end and the middle tier operation in the same server, okay? So it's going to require you to split them into separate servers. If you run it in the same server, it takes longer than if you run it in 2 separate servers. Okay? Questions? Yes?
So for Sam, you have a server for the front end and a server for the back end?
Yes.
One for each separately?
You will need at least 2 VMs, right? One for the front, one for the middle. But you can scale each of those layers separately. So you may have 1 front-end tier and maybe 4 applications, or maybe 2 front-end and 6 application servers. Any of those combinations can work.
In what case would you need more front-end than back end? I mean, how does it make sense?
So in a real system, typically, one of the reasons for splitting out the front-end from the app tier is that they're often very different pieces of software, right? The front end typically is a web server, right? And we think of things like Apache web server, but Apache is one of the older, nowadays considered less optimized servers, right? There's a lot of very, very efficient servers that can handle many thousands of clients on a single server for the front end. But they use some, very weird pieces of code, right? And so you keep those separate from your more general software that you run in your application layer, which might be running Python or some other language like that, right? And so you may need very few front ends, but you may need lots of application tiers. That's typically what happens in servers today. I guess if you have a system where you're mostly serving static content, which is something that the front tiers can do. Let's say it's a site with millions and millions of readers, but very, very little dynamic content. Then you may need multiple front-end tiers, and then the app tier is used only for generating dynamic content for the few cases, maybe the right cases, when you're writing new articles or something on a newspaper or something. So then you may need more front-end tiers and fewer app tiers. But I think for most services, typically the app tiers are considered computationally heavy, and you tend to scale those up sooner than the front end. Yes?
Why isn't there another load balancer between front end and app layer?
There could be, but typically what those load balancers are very specialized pieces of either hardware or software that actually are doing cross-layer things. So remember, if you took a networking course, you know that there's these different layers of the networking stack. So what these load balancers do, typically, all the stuff before the application server is running at IP layer. What these load balancers do is actually they sneak a peek at the higher layers. Right? They actually can see that, this is actually not just an IP packet. Not only is it a TCP packet, but rather it's an application level packet that's actually requesting an HTML request. And it can actually peek in there and decide, this is a new HTML request from a new client, and I can make a decision to say, this client from now on is going to be routed to this particular server. So that's a really, really complicated piece of machinery to do that. And it's very specialized to this one case of HTML requests, right? And so for a general thing like whatever RPCs you have between your front end and app tier, there may be no such hardware to do this, right? So typically you just do that in software. So your front ends may decide, yes, this front end is always going to map to this app tier, app server. Or it can say, yes, I'm going to do some sort of round robin. I'm going to put all the front end requests into a queue, and then I'm going to do round robin from that to the app tier. So you can do whatever you want in software. So the main reason is in the case of the load balancer, you're doing something at line level at a very high speed using specialized hardware. And that's why that's called out separately.
Will we have a central component in between these two?
You can if you want. That's up to you. So how you do the front end to the app tier protocol is up to you. So if you want a centralized queue, you can do that. I would suggest you not put it into its own VM because that's going to cost you. But you can certainly reuse an existing VM to hold that centralized component if you wish. Yes, in the back.
Do you need some kind of load balancing between the front layer and the application layer?
Yes, that was the previous question. Yes, you do, but it's up to you to deal with that. So if you need to balance the load between your different app tiers, you have to write the code to handle that. Other questions? Okay, so great. So now we have a service that can be scaled out on the front end, scaled out in the application tier. So what's left? What else can we do to make this system potentially faster? Yes? Database. But if you recall from there, I think it was probably in the scaling notes, databases are actually very difficult to scale out, right? Because they tend to do all these transactional things and things like that. They're notoriously difficult to scale out. You can try to scale them up, but you can get machines only so large, right? So what is one thing that could possibly help? Any thoughts? Cache, exactly. So one thing we can do, I'll come back to that, for checkpoint 3 is we can add a cache. So even with the database, a lot of the requests are still going to be just reads, right? Just read me what are the available products in this at the store. So a lot of those are going to be read requests. There's going to be only a few write requests. So if we can do a cache in between to handle the read requests, you can make things a lot faster. And so we're going to do this 4-tier system for checkpoint 3. So here you'll have to write the cache. It's a very simple cache. It's not like caching from checkpoint 2 or for project 2. It's a very, very simplified cache where we don't actually care about stale data. That's all perfectly fine. We just have to pass through anything that can modify the database and cache the reads. For both checkpoint 2 and checkpoint 3, we're going to have arbitrary loads. In particular, we're not going to follow the diurnal curve anymore. So even though we'll still provide you a time of day, just ignore it. You'll have to do something dynamically. So again, in this case, now your code has to not just scale based on a table that says this hour means this many servers. Now it has to actually look at the requests that are coming in, monitor them, and figure out how many servers it needs, or dynamically change the number of servers it uses in both the front end and the middle tier to get adequate performance. Right? And so you can monitor things like, how long does it take the request? What are the inter-arrival times of requests? You can monitor CPU load. But you have to be a little bit careful because a lot of these things are very noisy, right? The measures themselves are noisy. So one way to fix noisy measures is to measure over longer intervals, right? So if you, check over 20 seconds, you might get a better measurement than if you check over half a second. But now if you measure over 20 seconds, now it takes you longer for you to respond, right? So during that 20 seconds, you may have lost 10 clients. So now this is a kind of a tricky thing. It's a balancing thing. How fast do you want to respond versus how noisy a data are you responding to? So this is another case where even a small amount of non-determinism can actually make your system behave very differently. Right? So you have to be careful about these things. Okay. And checkpoint 3 adds one more complication that in checkpoint 2, we're going to give you an arbitrary load, but it's going to be a steady load. In checkpoint 3, we're going to actually have dynamic loads, which means it may start off low, and at some point in the middle of the run, we'll jump to a high load. Or it may start up high and then drop to a lower load. And your system has to respond to that. It's not just responding once to how the system is running, but rather over time it has to change. Okay? So in general comments, the amount of code you actually have to write for this project is actually relatively low. It's much less code writing than, say, Project 2. But mostly it's about things like benchmarking, deciding what you want to monitor, how you want to monitor, how to deal with non-determinism. Right? Those are the key factors in this. Another complication is in this project, actually, because it has to run long enough for us to make measurements on your system, Autolab is going to be very slow. I think each run on a completely free Autolab system takes about 5 or 6 minutes. So when Autolab gets busy, especially towards the end of the project, you may not see results for like an hour or more. We've seen in prior classes, it's 2 hours to get results of a run. So please, please don't wait till the last minute to iterate on your programs, okay? And so because of also, we're going to limit how many Autolab submissions because we don't want you guys to completely kill Autolab. So only 10 Autolab submissions before penalty comes in play. And remember, runs are going to be non-deterministic. But we're not going to allow you to say, oh, yes, I send it 3 times to Autolab. Can you get the highest score? No, we'll still take the last score, okay? So we can't play that game. The other part of it is there are bonus points available in this. So because this is not except maybe for checkpoint 1, but for checkpoint 2 and checkpoint 3 certainly, the scores are not all or nothing. Rather, it's going to be some score from 0 to nominal points or even higher than the nominal points for that part, depending on how well you do. So if you get really low number of unhappy clients with very low VM time, you can actually get higher points than what each part actually is supposed to get. Yes?
Can you explain the third point a bit? Because I thought we said for each new client, we open a new server, or opening a new server is like opening a new process. But the third point is...
No. So we're actually using processes to represent them, but we're pretending that these are VMs. So these are big, expensive things to start.
So a new process would be a new VM, right?
Yes. So
what exactly is the third point saying?
So remember, we're still pretending this is a VM, right? So you actually want a new machine, right? And so the fact that we can't actually give you a new machine is why we're using processes. But you don't have to worry about that part. You're just going to make a call to the library that says, get me a new VM. And it's going to boot the VM. And at some point, your process, your server, will be instantiated on that. And so all you'll see is that your server gets to run. Another instance of your server is running at some point in time.
So I think your caveat is don't use fork yourself.
Don't use fork yourself. It won't. I don't think it'll work. It'll crash and burn.
I think that's what you're saying.
Yeah, don't use fork yourself. Don't use threading either. You can't get around it by just adding more threads. It still won't work.
So you only use the VM
Use
call.
the VM call. Great. Don't try to create processes yourself. It's not going to help. Yes.
For checkpoint 2 and 3, will you check on that, right? For
So checkpoint 2 and 3 is you want to do the same procedure in terms of benchmarking. So you still want to have a good idea of how many, for a given load, how many servers you need for the front tier and the middle tier. So it's a little bit more complicated because now you have 2 tiers to worry about. But you can do that, right? So once you have that idea, now you have some code, right? You have your own code that's trying to do auto-scaling. Maybe it's monitoring some aspect of it. Maybe it's monitoring intra-arrival time, something like that. And so you try a heuristic saying, yeah, when we get intra-arrival times above this, I'm going to scale up my number of servers by this. Okay? You try to run it. And then you see, does it actually get to the number of servers you want it to? Let's say for a given load, you wanted to see 4 servers. You run your auto-scaling code, and yes, over time, it eventually gets to 4. Then that's good. What if it overshoots? What if it goes all the way up to 10 with that load? Then you know you have to tweak it down somehow, right? Okay. Similarly, if it doesn't get to 4, then also you need to make it a little bit more aggressive. Okay. The other aspect of that also you have to be worrying about is how long did it take to get there? If you wanted to be at 4, but it took 3 minutes to get there, that's way too long because our runs are only about 5 minutes long, right? So you'd want to get there as quickly as you can, but not overshoot. So there's a lot of the things that you can now, once you know what you want to get to, you can play around with it and see whether you can make your system get there quickly.
Okay.
That's how you do it.
In the load pattern, what is guaranteed to not change?
In which pattern?
In the load pattern.
Lower pattern.
Load pattern for checkpoint 2 and 3.
Oh, I see. Okay, so the question is, what is guaranteed not to change for the arrival pattern? So in checkpoint 1, the arrival pattern is going to match exactly that diurnal curve. In checkpoint 2, it won't match that curve, but it'll be steady through the run. So it may be a much higher load than you would have expected, but it's going to stay steady at that high load. Checkpoint 3 will allow for both high loads, low loads, but also loads that can change in the middle of a run. So it'll start low, halfway through the run, and then it'll jump up to something high. So that's the only difference between the runs. Yes. Okay, great. So one last question.
Sorry, so the relationship between the arrival rate and the amount like the server has to process, that's like fixed, right?
Yes, the question is the arrival rate and the number of requests handled identical? They're not quite identical. So the reason is that what we specified is the number of new clients arriving per second, right? But a given client may make a browse request, then make another browse request, then make a purchase request, right? So it can do a varying number of requests over time. So the number of requests that a client makes can also be random. So it's it's related to, but not exactly the same as the arrival rate of the new clients. And if you make your clients unhappy, they go away. So your request rate actually goes down.
Thanks, Bobby.
All right, thank you.
Okay, hold on. So if you've already collected your examples, you can leave. Okay, here to collect it.